Shaman King, if your spirit is strong, you will be the one. Okay, so we're here. We're going to talk about Ampere's law right now, which will eventually, by the end of us, bring us back to this equation that the B field at some distance away from a long, infinitely long wire is equal to mu naught I over 2 pi r. Okay, we're going to get back to there in a future video. What we're going to talk about now is just the introduction as to what are we thinking about when we use Ampere's law and what's going on, because technically there's some calculus here, but it's calculus that geometry students can do, which that's kind of a weird statement to say, but you'll see as we go along here. Okay, we're going to kind of also briefly talk about Gauss's law. It might come up in a second. And if you've seen Gauss's law, great, you know what we're talking about. If you haven't, well, whenever you go back in time to watch this video again, you might see it, or when you see Gauss's law later on, it'll be a very similar idea. Okay, so what we're going to be talking about is Ampere's law here, and what we're going to be doing is creating Amperian loops. Okay, and these Amperian loops can really be of arbitrary shape. So, you know, normally what you might see in a physics textbook is, let's imagine that I have some currents. Okay, so I've got a current going into the page, we'll call it I1, and a current out of the page, we'll call it I2. And I'm going to create an Amperian loop. Now, all an Amperian loop is it is some closed loop around these two currents. It does not matter the shape of the loop, only that it does not have any points to it, okay, because that messes up calculus. It kind of gets things weird. So it's a smooth, closed loop. So this, as a shape, is fine. Okay. Now notice I've also put an arrow here so I know the direction of the loop. The reason I have a direction of the loop is because if I take my fingers and I curl them in that direction, so right now my fingers would be curling like counterclockwise to go around this loop, the positive direction is the direction your thumb points. So in this case, coming out of the page, I2 would be positive and I1 would be a negative quantity because it's going in. So that is some Amperian loop I have just drawn. Now, one of the cool things about this Amperian loop and what we're going to see is that I can designate that the current I have enclosed in the Amperian loop is just equal to all the currents added together. So in this case, it'd be like I2 positive plus negative I1. Okay, that is the enclosed current inside of the Amperian loop. If I had another current out here, I3, I wouldn't care about it at all. Who cares? It's not in my loop. There's technically a nice calculus proof that you can show that when we walk around the loop, and we're going to walk around loops in a second, that this current's B field that will be created won't matter at all. But let's not go through that proof. Let's just assume that calculus works as it should, and that with a smooth closed loop, we will see that the current enclosed, or the total current enclosed in it, is just the sum of the currents physically in your loop, which is a kind of cool thing. Okay, so with that being said, what we're going to do for some current is we are going to create an Amperian loop. Now, since we know for a straight wire, we know the B field is going to be in a circular loop around this, it will actually be best for us that our Amperian loop is a circle as well. Because now our Amperian loop will sit directly on top of that B field. And for this Amperian loop, if we take a look at, we pretend this is the wire here, you know, it has the B field going in a circle around it. We're going to put our Amperian loop in that exact same spot. Whoop. The reason why we're doing this is, even though it doesn't look like a circle, it is. If we choose an interesting shape, such as a circle, it's going to make the calculus much easier to go through. And the reason why the calculus is going to be much easier to go through is because we are trying to set up the following equation. We are trying to set up the closed path integral of the B field dotted. This is a dot product. That's a dot product with some displacement vector. Okay? Now, what this means is that this current carrying wire is going to generate a B field. Okay, and let's say this B field is pointing in some direction up here. So let's look up at our original kind of weird funky shape. Let's just say the B field out here is pointing like this. I don't know exactly how it's pointing, but let's just say it is, okay? Our direction we're walking in the wire tangentially is this way, in pink. And this is the angle between them, in red. That's some angle theta. Well, for a dot product, what we actually have here is this is the integral of b times cosine of theta ds, where that theta might be changing the whole time because our loop is changing direction and our B field could be pointing in all sorts of different ways. And this makes life miserable. But if I take a B field and give it the shape of a circle, and over top of it, I place my Amperian loop, which is also in the shape of a circle, then what we will see is that at any point, the B field and the loop will be pointing parallel. And that means the angle between them will be 0 degrees. And we know that the cosine of 0 degrees is equal to 1. So I don't care about cosine anymore because I chose a clever Amperian loop. I chose an Amperian loop that was a circle centered on our current carrying wire. Okay? And it does get slightly more complicated up here as we look at things. But even if I have multiple wires, like I have here, there's no reason I still couldn't pick a circular loop. Because if I have a circular loop here, well, I'm still enclosing the same amount of current. Except this time when I do so, I can easily walk around the loop. So that's what we're going to do here. We're always going to choose circular Amperian loops. And what that will be is we no longer have to concern ourselves with this dot product. We now can just say that we have some closed path integral, so meaning we're walking in a closed loop. That is what this funny little circle on the integrand looks like. So we're walking in a closed loop along a B field through some distance vector. Okay? Now, at some radial distance, we know that the B field is going to be equal everywhere. So this B field is a constant, which means I'm going to pull it outside. And once I've pulled it outside, I'm going to say that, well, I just need to really integrate a closed path of a distance vector. And really, if I'm just integrating a distance vector, I'm really just asking myself, as I walk along the Amperian loop, how far have I gone? And if we look at this, that's not a hard question to answer. We know if we're looking at a circle, if I start here and I go all the way around and I come back, I know that distance. That's the circumference of a circle. That distance that we've gone, a circumference, or you want to call it S for a path, whatever, that's just 2 pi r, where r is the radius of the circle, your Amperian loop. I know that. So this calculus move right here, this closed path integral ds, I don't even need to do calculus. That is literally just saying, what's the circumference of your circle? Or rather, what's the length of your Amperian loop? And since you picked a circle, it's just the circumference of it. So we know that this is just going to be b times, well, 2 pi r. Okay, that wasn't bad at all. That was actually really straightforward and easy. Like, I didn't need to do any thinking at all in order to get that. So what we see is that this closed path integral b dot ds is just b times 2 pi r for a cleverly thought of Amperian loop. And the brilliant part about this that Ampere found out was that this will always be equal to mu naught, that permeability of free space for a B field, times the current enclosed within your Amperian loop. So if we went back and we take a look at what we had up here, where we had some, I2 and I1, well, if I wanted what the B field at some radial distance was, well, I would just be able to say that B times 2 pi r equals mu naught, and then the current enclosed, which in this case, I2 is positive, so I2, I1 is negative, so when I add them together, I2 minus I1, just like we did originally. Which means if you just want the B field itself, well, your B field equals mu naught times some current amount. We'll call it current enclosed here. We know what it would be, but it could be different from a problem, right? Divided by 2 pi r. And this once again shows us, hey, that is B of R. Mu naught I over 2 pi r. except this time we can do it for more complicated wire setups. Okay, so we get the same thing in the end. The real key is that this 2 pi r in the denominator here, that is literally just a circle that you're saying, oh, what's the length of the perimeter of my circle? What's the circumference? It's 2 pi r, and that's it. Okay, so important things to remember. The closed path integral of b dot ds is just equal, for our Amperian loops, to b times 2 pi r, and this will always be equal to mu naught times the current enclosed within that Amperian loop there. Okay, so that's how we do that. It's nothing too crazy. In the next video, we'll kind of go through this derivation again, and in a further one, we'll actually start talking about what else we can do with Ampere's law. We can start looking inside of wires themselves to look at a current distribution and a current density. So those will be in some future videos coming out. But until then, I hope you enjoyed this. Hope that really helped you out. It wasn't too crazy. It looks a little different, but remember, that's just 2 pi r. And this video is finished. Adios, take it easy.